if you're a software developer, you would like to have a good tooling around it that can automate it for you so you can quickly get results and look at your iteration in particular. So first off, a bit of a feature list, what our tool can do. So in order to get sound results, you need to put your application in a setup where you can get reliable, reproducible, and robust results. We do this by putting an application inside of a Docker container. So we leverage the Linux functionality to isolate the application to a certain degree. We pull the runtime metrics from these sources. So just going to go quickly over that, so because not everybody is dev. But I want to appetize the workshop a bit that we're doing later on. So you can get CPU, memory, network, CPU energy, DC energy, so RAM energy, there's also AC energy possible. It's a load of metrics. It graphs the data out for you, so you don't have to do that later on. And it applies some best practices. As you probably can figure, it makes a strong difference if your computer is preheated or if it's not, if your CPU is idling, or if you have a turbo boost or some other feature on, which maybe some of you have heard, but you can figure there's a certain difference in how you apply this. It's like you have a car and has different exhaust applied to it, considered tuning. So a PC can be tuned or it can be non-tuned. And we try to normalize this as good as we can. So here you can find a quick overview of how the tool generally runs in terms of like a flow chart. I specifically opted for making a flow chart, although I hated it in university, but I think it outlines the picture quite clearly. So you start with, on the left side, with the concept of this usage scenario that Jens has, to my knowledge, mostly introduced into the Blue Angel thing. And you have an architecture setup, so an application can consist of more than one Docker container. It can consist of 10 or so, if you think of microservices that interact with each other. And these are in configuration files, so think of text files, YAML files, whatever. You feed them into our tool, it orchestrates all these containers for you, and it measures them by querying these reporters that I talked about, so memory, AC power, DC power, etc. And just a bit of a different visualization if you think of how would I slice a typical application if I would be in the web. So in web environments, you typically have a user, so this is the Chrome browser on the right side, so you interact with the web application of any sort by going through the web page, right? And you fill out a form and you click on a link and you print something, etc. This would be your usage scenario, so your flow. But in order to provide this functionality on the left side, you know that there is more to the equation. So there is a server, and the server has a database, the server has a web server, etc. So we glue all this together by putting every one of these in a certain container as a microservice, and you can get for each of these containers, you can get the information out if you're in a web environment. However, since we're talking about the Blue Angel today mostly, I will show you what we have done in order to reproduce the measurements that have been done in order to get these certificates for Okular. So what the Blue Angel requires is a measurement that you do with it. And this is a tool that they have outlined in the specifications. So it's a power meter for AC power, which is very easy for a home consumer. So you can just plug your computer into this one, use the free tooling that is around in the GitLab repositories, and you can generate these readings in order to falsify or measure your own application. We, however, in our tool, we also have a lab setup, and here you see a bit of cabling, and the Blue Angel also requires a special machine because you need to fix it to a reference machine, because you can figure on a new M1 chip, you would get very different results than, for instance, for a older desktop computer. This is the desktop computer cut open, so you can get the DC power lines. Just showing you that there is two ways to get it. There's more, and we will hear that from Benoit later on, which is Intel RAPL. But these are the tools I wanted to outline here. And what you get when you run this usage scenario from our tool, and you can also maybe see this later in the workshop if this is your cup of tea, is that you get for all these digital input variables that Max mentioned. So for instance, you have the network on the top right, you have the DRAM here, you have the CPU right in the middle. So I'm looking at the orange labels. And you get this then also summed up, you get the CO2 ratio for it. So you have a snapshot view of what is really going on. Also, you need the view over time, which Max was also mentioning, you need the idle, right? So when an application is idling, you want it to not consume energy. So apparently, since there's other stuff running on the system, you can never really get to zero because otherwise the computer would be turned off, right? But you don't want to have any power spikes running while you're thinking that the application is idling. What you can see here in comparison is on the left side, you see the measurement that Benoit will present later. So this is the RAPL energy meter inside of the CPU. And on the right side, you see the energy measured directly at the wall socket. And why you see so many of these text nodes in here is, this is the usage scenario. So here, for instance, it says, I'm starting an action going into presentation mode. Here it says, I'm starting an action also going into presentation mode. And here it says starting an action and I have to stay back to see it. So this is turn left and right. So here the PDF was turned left and right. And with our tool, you can see that over time. So I use this view, for instance, to spot idle energy. And I use this view to compare certain code paths against each other. So here you can see on the left side that the presentation mode has a different energy profile associated with it than, for instance, turning left and right. So turning left and right takes more time, and the integration of the curve would be more energy consumed for an action. So as a developer, you can now say, shall I have a look into that because it consumes generally more energy? Or is this fine because it is a tougher action to do, right? The CPU just has to do more work because there's more compute to be done. Depends on the application, obviously. And this was the quick tour. As Max said, we just want to give you quick knowledge in very small chunks, and talk to us later on if you're interested in this topic in particular. So thank you.